All right. Well, thank you, Curtis, and to everybody who's involved in planning CocoaHeads. I appreciate the opportunity to come speak. So I've actually started coming to CocoaHeads back in like 2012, I think. And at the time, I was just doing iOS as like a hobby kind of thing. And I thought that I had kind of missed the boat. Like I thought like, oh, this mobile thing, like that's not cool anymore. But I was interested in it, so I came and luckily was very wrong. So coming to the group, I really was able to level up and learn, and ends up now that I've been doing iOS full time for over 3 years. I run a small software consultancy called Scopelift, and so it was definitely not too late to the tech. But tonight I want to talk about a different kind of technology where there's no doubt that you're not too late to start learning about this. It is very early days in the blockchain and cryptocurrency world. So I'm hoping to present to you something a little bit different from what you're used to learning about, and maybe introduce you to this world of blockchain and distributed or decentralized apps, which people are calling dApps. So before I get started, here are some places where you can find me on the internet. Always love to chat, so if we don't get a chance to talk tonight, feel free to shoot me an email or ping me on Twitter or whatever. I always love to connect with people and discuss things. So what I want to cover tonight, first of all, I want to start just with a general idea of what a dApp is, and specifically how kind of a dApp functions in the context of what a blockchain is and what a smart contract is. So you've undoubtedly heard those terms. There's a bunch of hype around this stuff right now, but really just try to, it's going to be a bit of a whirlwind, but go through the understanding of that tech and hopefully come away with getting past the hype a little bit, actually understand the technical aspect of what's going on here. It's really actually not that hard when you look into it a little bit. So once we have an understanding of what a dApp is through these other more fundamental concepts, then I want to talk a little bit more nuts and bolts about how you would build one. And there are some specific tools that exist today that I want to talk about, and then also just do a brief comparison to developing apps for iOS, which is what we're all used to. And then finally, I want to finish briefly tonight with why you would want to do this, why you would want to build a decentralized or distributed app in the first place. And it might seem like that would be the good place to start, right? Like, don't you want to understand why you're doing something before you talk all about it? But actually, it turns out the reason that you should want to build a dApp is because the technology, the properties of the technology of blockchain, of smart contracts, they bestow on you certain unique abilities that you want to take advantage of if you're building a dApp, right? Today, we're in the middle of a hype cycle around this technology. So, throw blockchain in your startup's name and double your valuation, do an ICO, like that whole thing is going on. But really, you shouldn't do that. You shouldn't use a blockchain. You shouldn't use a smart contract. You shouldn't build a dApp unless you understand the technology and you know that the trade-offs that are involved and the properties that the technology gives to you are what you are after, what you can, the value that you want to present. So that's where I want to kind of finish the talk tonight. So what is a dApp then? Well, a decentralized app is really just an application that stores some of its code and some of its state on a public permissionless blockchain. So obviously, right? Well, let's go a little bit deeper though. Let's try to understand this a little bit more. What is a blockchain then? So it turns out a blockchain, for all the hype, is really just a data structure. And it's a pretty simple data structure, actually. It's a data structure that's similar to a linked list. So in a linked list, you have a bunch of data, and each data is in a node. And the node, in addition to storing the data, points to the next piece of data in the list. So in a blockchain, you have what's basically a linked list, where we call the nodes blocks. And each block has a unique hash of the data that it contains. And it also includes a reference to the previous block's hash in its data. So let's go even deeper down the rabbit hole. Oh, obviously, right. Let's go even deeper down the rabbit hole. So what is a hash function? So a hash function is a deterministic, one-way cryptographic function. And what it does is it maps arbitrary inputs. So any sequence of bits, no matter how long that sequence is, you put it into a hash function, and you get out a fixed length sequence of bits of a known size. And there are some other important properties. So there's no predictable correlation between changes to the input and to the output. So you change one bit of input, and the output that you get out is completely different, completely unpredictable compared to what you put in. And again, it's one way. So if you're given the hash of something, there's no way to take that hash and derive the data that went into the function unless you just guess a bunch of stuff and compare it. So if you were to take the string hello world and you were to calculate the hash of that, what you end up with is this long string of digits and letters. What this actually is just a hexadecimal representation of a sequence of bits, right? So it's a big hexadecimal number. Now we just add a comma, so now it's hello world instead of hello world, and we get something completely different out. No correlation between the two, even though all we've done is add one character to the input. Similarly, you could take the entire text of the King James Bible or whatever religious text you prefer, and you could hash that, and you're going to get a string, another set of bits of the exact same size as if you hashed a tiny string or a single character. And again, no correlation between the input and the output in terms of it's deterministic, but there's no correlation in that if you changed one character of that input text, even if it was maybe terabytes in size, you could hash something that was terabytes in size, change one bit, got a same size output, but completely different bits on the output. So those are kind of the important properties of a hash function to understand. And probably a lot of you already knew that, right? So how does that play into a blockchain? Well, in a blockchain, each block has to have what we call a valid hash. And a valid hash is really just something that is defined as starting with the correct number of zeros. In other words, it's a hexadecimal number that is less than a certain value. And finding a valid hash for a set of data that's stored in a block requires taking that data and manipulating it slightly, and then guessing and calculating the hash and seeing if it starts with the right number of zeros. And if it doesn't, you guess again and you calculate again. So the final property of a blockchain is that each block has to include the hash of the previous block. So let's take a look at what this would look like. So here would be the first block in our blockchain. So we're storing the fact that this is the first block, the Genesis block. The pointer to the previous block, the reference to the previous block hash is null because it's the first block. The data that we're storing in the block is just hello world. And then there's this weird property called a nonce. That stands for number used once. That is the piece of data that you actually manipulate to find a valid hash. So you just add this number onto the end of the data that you're encoding or hashing, and you keep incrementing it and calculating hashes until you get a hash that starts with, in this case, we're calling a valid hash 2 zeros. So here's our first block. It's a valid block. And now we add another block to our blockchain. So this block stores the data foobar, just another string. It also has now the reference to the previous block. So it stores the hash of the previous block. It stores the fact that it's block number 2, and it has the nonce that proves that it's a valid block number. So anyone who was looking at this blockchain could take the data, could take and hash it. So hashing is, calculating one hash is relatively inexpensive computationally, and validate that the hash was a valid hash. And so you can kind of keep adding things to your blockchain, keep storing additional data, calculating valid nonces, and you end up with this long string of blocks. So this is it. I mean, this is the data structure of a blockchain. All the hype is really about this. And the question you might be asking yourself is, why? Like, why would you do this? What is interesting about this? What properties do you gain? So blockchains, when constructed like this, give you some interesting properties around security, specifically around data that is relatively tamper-proof or is computationally expensive to tamper, and very auditable as well. So let's look at why this is. Here's our blockchain that we built in the last example. We have 4 blocks. And now let's say that someone wanted to surreptitiously go back and modify the data stored in the very first block. So let's say that we wanted to add that comma back into our hello world string. So we, as the attacker or someone trying to secretly modify the data, we go in and we add the comma. But what happens is now the hash of this block's data is no longer valid. And so anyone who is trying to look at this blockchain and ensure that the data is valid, it's going to be very obvious to them very quickly that something has changed. So maybe you, as the attacker, you say, well, OK, I can fix that. I'll calculate a new nonce, and I'll guess a bunch of hashes until I find a valid hash. So you do that, and now it looks like you've gotten away with it because it looks like your blockchain is correct again. The problem is that the next block in the chain has a reference to what used to be the previous block's hash, and that has now changed when you've recalculated. By definition, it's changed because you've changed the data. So anyone, again, auditing this blockchain is going to immediately know that something is up, that this data has been tampered with. This is not a valid blockchain. And so maybe as the attacker, you say to yourself, all right, well, I'll update the hash. I'll calculate a new So now the block is invalid, right? I updated the hash to point to my block, but now the hash of the second block is invalid. So what you realize is that to fix this block, you have to calculate the block, a new nonce, a new hash for block number 2. Once you do that, now block 3 is broken, now block 4 is broken, etc. Right? So in order to manipulate the data in block number 1, you end up having to guess and calculate hashes for every block after that block. And after a certain point, if the difficulty, if the hash level that's required for the block is high enough, this becomes extremely computationally expensive, and at a certain point becomes completely computationally impractical. It just becomes impossible to do this. So this is how a blockchain gives you tamper-proof, or very auditable, safe data storage. And this is the basis for all the hype that you've probably been hearing. So now we have an understanding of our blockchain basics. Where, though, do smart contracts fit into this? And actually, there's something else that I haven't mentioned yet, which is the idea of a cryptocurrency. So let's talk really briefly about a cryptocurrency and then how a smart contract fits in on top of that. So in a cryptocurrency, the data that you store in the block is just value. In other words, it's a list of transactions between participants in the network. Now, some of these transactions end up being rewards for finding a valid hash. So you go through the work of guessing a bunch of nonces to find a valid hash, and if you find one, you get the right to include a transaction in your data that pays some Bitcoin or other cryptocurrency to yourself. But all the other hashes or all the other data stored in a cryptocurrency blockchain are just regular transactions between users. So your blockchain ends up looking like something like this. The data that we store are just these lists of transactions. They include mining reward transactions and then just normal transactions of users sending value to each other. And because the data structure is tamper-proof, and because anybody can look at the whole blockchain and kind of add up incrementally how much of the value any user has, you can basically ensure that no one is able to double spend, right? If you try to spend something that you don't have, anyone validating the blockchain is going to be able to tell that you never had that value to begin with. You're not able to send it because you never had it or you already sent it to someone else in a previous block. So this is how a public permissionless blockchain with a cryptocurrency works. We've kind of talked about how mining works and provides the security for that. And now with a smart contract, we just kind of add one more layer to that. So in a smart contract platform, it's not just lists of transactions, so sending a value that we include in the data, but we can also include any arbitrary code, so instructions that can be executed, right? So we can include code that is to be stored in the blocks, and then we can also include in our transactions instructions to the miners to execute code that we've deployed and stored in previous blocks. So the miners then, when they're trying to assemble everyone's transactions and find a valid hash, they'll execute your code, and it will determine, the output of that code will determine the final state of the data that they're going to store in their block. And executing that code can include doing things like sending value, so it can be like programmable sending of value, or it can just be storing arbitrary data to the blockchain itself. So you end up with a blockchain that looks like this, where your transactions, your list of data, are not just regular transactions, but also transactions for doing things like deploying code and executing code with side effects as a result. So are you guys with me so far? Is this making sense? Yes. Cool. So with that, we've kind of put into context what smart contracts are, how they fit into the idea of blockchains. And so basically what a dApp is then is some kind of application where at least part of your logic lives in a smart contract and part of your state is stored on that blockchain. So cool. How then do we go about building a dApp? Sip of tea. So right now, the most popular way to build a dApp is to write a smart contract using a language called Solidity. So this is just a programming language. We'll talk a little bit more about it. And then we deploy that dApp to a public blockchain called Ethereum, and we interact with it via a library called Web3. So obviously, right? Let's dig into each of these one by one. Ethereum is the second most popular blockchain in cryptocurrency. If you've heard of a cryptocurrency, you've probably heard of Bitcoin. If you've heard of more than one, Ethereum is probably going to be the second one that you hear of. Ethereum is not just a clone of Bitcoin. So a lot of these alternative cryptocurrencies that exist, they just forked the Bitcoin source code and they made some minor modifications to it. Ethereum came much later than Bitcoin. It was launched in 2015. It took a lot of the lessons that people had learned about cryptocurrencies and blockchains since the introduction of Bitcoin, and it added a bunch of interesting new tech and research to it. So there's a lot of reasons why Ethereum is interesting, but its real reason for being is to be a smart contract platform, and that was built in from the ground up. So as a result of that, Ethereum has a virtual machine, a VM, kind of like the JVM, and that VM has its own native assembly language that is full Turing-complete programming language. Anything that you could imagine programming, you could compile down to the assembly that runs in the EVM. So given that, we have a programming language called Solidity, and this is the most popular smart programming language that there is today. There are definitely others, so similar to the JVM where Java compiles to JVM bytecode, but you also have things like Scala and what's the new one called? Kotlin that can compile down to it, right? So similar to that, you can have other languages, and there are, but Solidity is by far the most popular. So Solidity compiles down to EVM bytecode, and as a language, it's statically typed. It has like a C-like syntax, and it's what I would call contract-oriented. And what that means is it's very familiar and similar to object-oriented programming. It feels a lot like that, but the primitives that you're building aren't classes, they're contracts instead. And finally, Web3. So Web3 is actually just a JavaScript library for interacting with your smart contracts. You can do this directly just by talking to the nodes, right? They have like a JSON interface, and you can talk directly to a node via the JSON interface, but most of the time today, again, very early days, but most of the time when people are building interfaces, they're doing it on the web, and they're using this library. So in particular, Web3 is designed to work with a Web3-enabled browser. So there are specific standalone browsers that do this, like Mist, but there are also browser extensions like MetaMask for Chrome and Brave that allow you to interact with your dApp. And the big thing that these extensions do is that they prompt the user to sign any transactions that involves the movement of money, right? So you have your private keys associated with your wallet. That's all stored in the browser extension. You, as the developer of the dApp, never get to touch your user's private keys. Instead, you just make a call to some function, and then the extension or the browser prompts the user to sign that transaction for you before you then send it off to the Ethereum network to become part of the blockchain. So let's look at a quick example of some Solidity code. That first line is just a compiler directive telling you what version of Solidity to use. And then the idea behind this contract, so you see this is a contract, not a class, is that we're building a little billboard on the blockchain, right? This is our startup. We're going to do an ICO, raise a couple $1 million. I'm kidding. So we're storing just a message on the blockchain. So we declare this public property that's a string called message. And when we declare it as public, what we're saying is that anyone can read this value, this data that's going to be stored on the blockchain. Not anyone can set it, so that's different, but anyone can read it. And now we have a constructor. So it's similar to a constructor in an object-oriented language. The big difference is that this constructor only runs one time for a given contract, and that's when the contract is actually deployed to the network, right? So unlike in object-oriented programming where you're very frequently creating and destroying objects all the time, with contracts, you usually just deploy it once, and then it's out there forever, right? And you're never destroying it, and you're not doing that frequently, deploying it. So you provide an initial message to this constructor, and basically what the constructor does is it sets up the initial state of the contract. So we're also defining a fee that we're going to charge users in order to update the billboard. And then we have this public function. So this is a function that can be called by anyone. It takes a parameter that's a new message. It's public, called by anyone, and then it's payable. So that little modifier there at the end says that it's payable. And what that means is that a user can send Ether. So they can send value in Ethereum to this function when they call it. And what this first line of the function does is validates that the user has paid exactly the fee that you're expecting. And if they haven't paid that fee, if they haven't sent that along with their call to the function, then the smart contract will cease operations. That's what the require directive does there. But if it does, then they'll go ahead and update the message to whatever the user has decided they want to show on your billboard. So now we have our smart contract in Solidity. We deploy that to the blockchain, right? We compile it, deploy it. It's up there now, so how do we expose that to the world, and how do users interact with it? So again, the first thing that you would do is just write a standard web front end. So you can use whatever JavaScript framework is popular this week and use HTML and CSS, and you build a front end that shows the value of the billboard and also has an interface for the user to type their own message and buy the billboard if they want to overwrite it and own it. One last thing I wanted to touch on that I didn't really make clear when I was looking at this Solidity sample code. So you might be saying to yourself, like, I thought blockchains were immutable. Isn't that what we just talked about? Like, when you store data on the blockchain, it should be there forever, but it looks like we're mutating that message by updating it. So you're right, data on the blockchain is immutable. What we're actually doing here is we're not saying erase the previous value. We're saying the current value will now be updated to this message. So it's all auditable. Anybody can go back and look at the history of every message that's ever been stored in the billboard. But if someone asks for the current value, they're going to get this message that we set in the function. So that's what's going on here. All right, so here's some Web3 code. I won't go through this line by line. It's just JavaScript using this library. Nothing particularly remarkable about it, except some specific things that allow you to interact with the blockchain. So you have to tell the library what address your smart contract is deployed at. So the address is something that's given to you by the network when you deploy the code. So it knows where to go to run it. And then you can do things like pull the data from the blockchain. That's free and happens pretty quickly because it's just like a standard network call. You're not modifying any state. But if you want to send value or modify state on the blockchain, you're going to pay a fee. And so that has to include a signed transaction by the user. So that function at the bottom there, that update message function, you could imagine having that wired up to your interface when the user clicks the buy button. And if you've done that, someone can come back to here to your dApp, and they could type the message that they want and click that buy button. And then they're going to be presented. So this is MetaMask, the browser extension. All the interfaces are very similar for these different browsers. They're going to be presented with an interface like this. And again, I won't go through everything that this interface is showing. It's honestly more complicated than it needs to be. Usability is definitely something that needs to be worked on in the space. But it's telling the user, like, here's the amount of Ethereum you're sending. Here are the fees that you're going to pay for that. And it gives them the opportunity to reject this transaction or submit it and sign it. And if they submit it and they sign it, what's going to happen is that's going to get sent to the blockchain, and you'll get a callback when it's complete. And now you've bought your billboard, and you can advertise slopes on the blockchain. So we've kind of walked through the nuts and bolts of how to create a smart contract using the most popular set of tools today. Just real briefly, a comparison to iOS app development that we're all used to. Sure.
So Web3, would that be like using Express as your backend? So how exactly does Web3 work? Which layer does it have?
Good question. So where does the question is, where is like Web3 in the stack, in your layer? It's all on the front end, right? So it's a JavaScript library that is just part of your front end web stack. So in the example that I gave with the billboard, you're writing a front end web application just like one that would communicate with a server and an API like you're used to communicating with, except instead of communicating with a server API that you control and exposes some JSON interface, instead you use the Web3 library, and it's communicating with a node on the blockchain instead. So that's all that's going on there.
Can you do it yourself without Web3?
You absolutely could. Yep, you could just have the nodes just speak JSON, so you could just talk JSON to that node and write and send data. But then you have to think about things like signing transactions, managing private, public keys, things like that. So what the extensions and in combination with Web3 give you is a kind of unified user experience around those problems that you would otherwise have to handle yourself. Yep.
So how do you actually write this stuff, debug it? Is there like a test environment, blockchain you can use? How do you do this without creating a bunch of
Yeah, great question. So there are So there are test networks. So they're like the same source code that runs the full blockchain, but they're just test nets. They don't have any real value. You can get people to send you Ether on these test nets for free, right? They also have tools now it's like a local. It's basically a mock of the interface for the blockchain, right? So you run it locally, and it acts like the blockchain is going to act. It pretends to mine your data and do all that stuff, so that during development you don't have to talk to some external network. You just talk to some program running on your PC that behaves like the network would.
There's Ganache CLI and TestRPC.
Yep, Ganache CLI is one of them, and TestRPC is the other. Exactly right. Any other questions about that technical stuff before we move on? Happy to do it now. Cool. All right. So brief comparison to app development. So kind of like I mentioned earlier, this space is just so early. It's so early. There's so many things yet to be worked out. And there are a lot of things that go along with that, as opposed to iOS app development, which is now 10 plus years old. You know, when you work with someone who wants an app, they have an idea of what an app is, of what the properties of an app are. You know, people use apps on a day-to-day basis. None of that is happening yet in this ecosystem, so everything is up for grabs. All of these tools, down to the blockchains that are popular themselves, could be completely different in a few years. We just don't know. So as a result of that, one of the consequences of that is that the tooling has lots of rough edges. If you spend all day in Xcode and you're like me, you probably curse at it several times a day and think to yourself, like, why can't this stuff be better? But actually, when you go and work in a really nascent ecosystem like this one, you realize we don't have it as bad as we think we do. The tooling's actually pretty mature, and it can get a lot worse. And that's not a knock on any of these projects. Like, again, this is also early. Everything is being figured out. And there are actually some organizations that are doing some really, really good work to make that tooling better, and it's improving at a very fast rate. So for now, if you're doing this development work, you're going to be using the web stack. Like, that's pretty much the only thing that's out there right now for dApps. But I think that's just for now, right? Like, people are going to want native decentralized applications if these really become a thing. And the reason that we don't have a good way to deal with that right now is just because no one has figured it out. Because it's, again, going back to the fact it's just so early. So how do you manage transaction signing and private keys and wallets across multiple native apps? Like, all of those are open questions that I think are super interesting and need to be explored. But for now, you're using the web stack. The other thing is that there are like no gatekeepers, and this is like the purest form of a permissionless development environment that you can imagine, right? Like, you know, people say that the web is open and permissionless, but you still have certain gatekeepers on the web. Like, you know, you have to register your DNS somewhere and do these there are certain centralized aspects to the web even. These blockchains, like, no one can stop. Like, if you want to write a smart contract and deploy it, literally no one can stop you from doing it right now, short of attacking the entire Ethereum network and taking it down. So that's a good thing and a bad thing, but it's certainly different from iOS, where we have things like app review and guidelines and all these sorts of things. The other thing is that money is on the line. I mean, by definition, this is, you know, cryptocurrencies, it's programmable money. So you want to be real careful about how you're writing these contracts. Similarly, once you deploy a smart contract, you cannot change it. It is deployed, and that is it. So if it has a bug, that bug's there forever. If it has a security flaw and someone can exploit that, you can't stop them from exploiting it. It's done. So auditing your code, making sure that it's right, thinking about how you want to pre-program the ability to update parameters or logic in your code before you deploy it. Like, if you want to have some kind of delegate pattern for a part of the logic where you call into another contract and you can update the address of that contract, all of that has to be figured out before you launch your contract to the mainnet and launch your product. Which is a lot of pressure. And so, you know, auditing of smart contracts and, you know, the whole process around development is again, something that's still being figured out and is very early days because it's a very different kind of mindset and paradigm. All right, so we've gone through some of those nuts and bolts, did a comparison to iOS. So now I think we have enough information to actually kind of tackle this question of why you would want to do this in the first place. And as I kind of alluded to earlier, the reason you should want to build a decentralized app or a distributed app is because the properties that are inherent to blockchain and smart contracts are going to allow you to do something new, something that wasn't possible with a traditional platform. So just don't try to shove blockchain into your existing app or your existing idea. By definition of the fact that it's an existing app or idea, it probably doesn't need a blockchain, right? Like, what's interesting about this tech for me, the reason I'm kind of excited about it, is because I think on a long enough time scale, it has the potential to unlock all kinds of new things that we haven't even thought of yet. Like, in a lot of ways, that's what the internet did. Like, there's all kinds of things we take for granted today that were literally unimaginable until we had the internet, until we had widespread adoption of the internet, right? You know, Uber and Airbnb and social networking and a million other things that just make no sense unless you have the internet and mobile phones in everybody's pocket. And I think that, like, there's the same kind of potential here, but you have to know what the tech is all about. And so we've gone through some of that now. And then you have to find applications where you can do new and unusual things given those new possibilities that are unlocked. So this one actually should be obvious. Right now it's not obvious because we're going through this hype cycle and people are just trying to shove blockchain into everything. But I think that's going to shake out in the long term. So when might you want a dApp? Well, if you need digital scarcity, right? Before blockchains, digital scarcity was not a thing that was possible. Now it is, right? Programmable money, like fully programmable money, not just like an endpoint where you can receive payments, but you can put logic around money to make it do whatever you want it to do. That's new, and that's something that wasn't possible before. So if you have some kind of application that would benefit from digital scarcity and programmable money, you might want to build a dApp, because you can't do that any other way. Similarly, tokenization, so digital assets, so turning assets into digital representations. A couple of examples. So software licensing. Right now, it's just like a row in a database somewhere on somebody's server that says you have a license to this software. That's something that could easily be tokenized, and I can see that being one of the initial use cases. So it's a digital asset that you own and control with your private keys. Equity is a similar thing here, right? We have this whole system based on contract law and paper to own stocks and equities in companies and startups, right? All of that can be turned into tokens. All the rules around that, or many of them, can be tokenized. Things like vesting of shares over time. All of that can be done programmably, along with probably a whole bunch of other stuff that we're not thinking of. So if you would benefit from some of those kinds of properties, you may want to dApp. So if you really need data to be stored in a tamper-proof and auditable way, a blockchain is a great use case, right? And there are some like really obvious use cases here that we're already seeing people experiment with, right? So we've seen governments publish certain data to the blockchain as a way of greater transparency to their citizens, and a way of proving things are out there in a tamper-proof way. So there are a lot of possible applications where you really need data that can't be tampered with to be stored somewhere that anybody can look at. And if that's something that would be useful, you may want to build a dApp on the blockchain for it. And finally, this is kind of the one that is the most interesting to me, and I would say the least explored, and that's the idea of trust minimization. In particular, what I mean is that with blockchain technology, with dApps, you have the ability as the creator of the system, so the developer, the owner of the system, to limit what you can do. And not like an artificial limit, like we promise never to do this, but actually a provable, definite limitation on your own capabilities. And it may seem funny to want to do that, but there are actually a lot of cases where I think doing that can provide value to the product or service that you provide for your users. So a couple of like really simplistic and obvious examples. Again, I think the most exciting examples are things that we can't even imagine yet. But a couple of simplistic examples would be like an escrow system, right? So in a traditional escrow system, two parties and a trusted third party to mediate it, you have to give the money or the asset to that trusted third party. And they hold it, and you have to trust them not to run away with the money, but instead to hold it until some dispute has been mediated, and then they decide which party gets the escrowed balance, right? With a smart contract, you can build an escrow system where a third party still gets to decide who gets the money or the asset, but they never control it. They don't have it. They don't have the ability to run off with it, right? It's locked in a smart contract on the blockchain. They simply have the ability to press a button that says it goes this way or that way. So that is a valuable property in an escrow system, right? It would reduce the amount of, say, oversight that was needed on escrow companies. It would reduce the probably the cost of an escrow service, because you don't need things like insurance and legal disputes and all these other things, right? Or as many of them, right? Another kind of trivial example, but say you're developing a massively multiplayer online game or something like that, right? And you're going to have some kind of assets or resources in the game that can be harvested or collected by users. You can encode the mechanics around how those assets are distributed into a smart contract on the blockchain, and give assurance to your users who may spend hours of their life playing this game and collecting these assets, that you're not going to kind of pull the rug out from under them and change the game mechanics at some point so that their assets become useless or less valuable or whatever. Again, kind of a silly example, but it shows that I think this is like an unexplored space of how we can use these tools to actually limit our own abilities and minimize the trust that our users have to have in us, and actually provide value and unlock new possibilities. So that's probably the piece that I'm the most excited about. All right. So the last thing that I'll close on real quick, we don't have to go through all of these, but is anyone actually doing this? So the short answer is actually not really. I mean, it's really early in the space. There aren't a ton of examples of widely adopted projects, but there are a handful of things out there that are kind of proving out these concepts in interesting ways. So the Brave browser you may have heard of. It allows you, it's a privacy-focused browser. It's just it's a standard web browser. But the interesting twist here is that they have a token, a custom token on Ethereum that is called the basic attention token. And as you browse, websites can be paid out in tokens for your attention, right? So it's kind of a new twist on this, trying to create like a more sustainable model around content creation. I'll mention just a couple other ones of these. Gitcoin is kind of interesting. So it allows you as an open source developer to post a bounty for an issue on GitHub. And then when the user completes that issue to your satisfaction, they're automatically paid out in Ether or in a token on the Ethereum network for the work that has been done. So this is an interesting one and actually has a decent amount of adoption, decent amount of activity because it's, it's focused on techies and developers who can kind of figure this stuff out and know what they're doing, which is where we're at in the space right now, to be totally honest. CryptoKitties, you've probably heard of if you've heard about the space at all. It's like a game where you breed digital cats, but they're scarce, rare digital cats. This isn't my cup of tea, but like I don't collect Beanie Babies either. So, there's obviously collectibles are a thing, and this is like collectibles with a twist, this game level on top of it. So it's an interesting use case, and we actually may see a lot more of it over time. And to that point, I'll just point out one more, and that's this company Hyro here. This is actually a couple of local Philly folks who are doing digital art on the blockchain. So scarce digital art where some aspect of that art is stored on the blockchain. And they have like a few interesting twists on that. They're in beta right now, but they're getting ready to launch to the mainnet. And like I said, it's a couple local Philly guys that are developing that application. So it's pretty cool. All right. So yeah, I mean, that's basically it. I hope through this talk that I've at least kind of given you a better understanding of what this stuff is all about. If I've whet your appetite a little bit and you would be interested in learning more, I do help co-organize a meetup focused on blockchain stuff, specifically aimed at developers and technologists. So it has like more of a technical bent to it. We don't talk about investing or the latest, greatest cryptocurrency that you should buy or anything like that. It's more focused on the actual technology. And so you can check that out. I would love to have you join. We actually have one next Thursday. There's a waiting list, but we always have people drop off. So you can get on that. I bet you'd be able to come. And then, so I've been spending a little more time myself learning about this stuff and trying to start putting together some resources aimed at developers. So I have this site, buildblockchain.tech. I do a newsletter every week now, trying to have a technical focus on blockchain stuff, really just trying to like get through the hype cycle that we're in right now and actually get down to the tech that underlies it, which to me is very exciting, and again, on a long enough time frame, I think is going to be pretty important. So yeah, check that out if you're interested. You can follow along with what I'm doing there. And that is it. I've been droning on and on here, but I would be happy to take questions if there's time.
Hey, could you elaborate on digital scarcity? I kind of know what you mean, but I feel like you mean something else by that.
No, you probably, so the question is, can I elaborate on digital scarcity? What exactly does that mean? It's probably exactly what you think, right? So typically one of the features of things being digital is that you can make infinite copies of them, right? So if I have a Word document or a text file or a piece of code, like I can make a copy of that code and give it to you without giving up my copy, and now you have a copy and you can make a copy, and those copies are basically free. And that's good. That's one of the properties of digital systems that made them so revolutionary. But then it introduces this new problem. We don't have anything scarce in the digital world. And so Bitcoin and assets in general introduce the idea of scarcity back into a digital ecosystem in a native digital way. And that's a new thing that we haven't really come to terms with what that really means yet. So that's all I meant by that. Tong?
A chain has a start and then it has a link. How is that structured? Like, does everyone start their own chain? Are there a billion chains out there?
Yeah, great question. So the question is like you have a chain and it starts, and then how does everyone get the chain? Like, are there a bunch of chains out there? So there are a bunch of different blockchains that represent like different cryptocurrencies, right? But for any given blockchain, like say the Bitcoin blockchain, every node that participates in the system has a full copy of all the data in the blockchain. So they have all the blocks going back to the original Genesis block, and they store each of those, and they verify each of those themselves. So for Bitcoin, for example, there are about 10,000 nodes worldwide that run and do this all the time. In addition, some number of those nodes are what are called mining nodes. So they're running a bunch of calculations to try to find the next valid block, doing those hashes, that guessing and hashing that I mentioned before. So this is a thing you might have heard about, like takes all of the energy, and it's kind of controversial, but that's what the hashing is. That's what those nodes are doing. They're doing this hashing, trying to find the next block so that they can include in that block a reward to themselves in newly minted, newly created Bitcoin. But every node creates a copy. You don't have to run a full node to interact with the blockchain, but you do have to run a full node if you want to verify every transaction in the chain.
How long is it?
Good question. So right now the Bitcoin blockchain is about 143 gigs in size, or maybe it's probably about 150 by now. That's probably an outdated number. So each block is somewhat controversially 1 megabyte in size. So you can do the math there. It's a lot of blocks. But yeah, so a new block is created about roughly every 10 minutes. Different blockchains have different properties, but that's the Bitcoin story.
Could you show a quick example of the JSON interface?
I actually don't have anything really ready right now for the JSON interface. It's pretty unremarkable, though. It's kind of just like a JSON interface that you would interact with. So this is specifically the Ethereum JSON RPC interface that you communicate with the node with. It just looks like any kind of server API that you would interact with. So nothing particularly fascinating about it.
How is this scalable? Like if this is growing at 10 minutes, like you said, 1 gig for 10 minutes.
Yeah.
Like in 3 years, this is going to be
Right. So the question is, how is this scalable? The short answer is right now it's not. We're trying to figure that out. So it's 1 megabyte every 10 minutes. That still certainly adds up over time. Right now, so the trade-off that you've kind of recognized, Amit, is that you have to decide between how many transactions you can fit. So if the blockchain grows faster, you're adding more data, and you end up with a really huge amount of data really fast. But if you don't allow the blockchain to grow faster, then it's slow, right? Bitcoin right now only has room for, it can only handle about what works out to be when you do the math, like 3 to 7 transactions per second, which is really not that many if this is supposed to be a global network. Things like Ethereum can do a little bit better, but only like maybe 1 order of magnitude better at best, which is still not really good enough, especially when you think about the fact that Ethereum is supposed to be a smart contract platform for running all these applications. So we haven't figured out how to scale this. There are a bunch of different possibilities. There's something called layer 2, something called on-chain scaling, a bunch of competing ideas. A lot of people get really angry about whether their solution is better than other people's solutions. It's what makes the space so interesting. It's crazy, and everything is being figured out right now. So doesn't scale, trying to figure out how to scale it.
Hash graph.
No. Zorn.
Is there a lot of security problems with people like DOSing the network or trying to? You said there's a limit on the payload. But
Yeah.
I can imagine if there's a blockchain that accepts a larger payload.
Yep.
People sending just noise.
Yeah, absolutely. So the question is about like DDoSing the network, and how do you deal with that? So different blockchains have different properties. So Bitcoin is built in such a way that there's really, it's very difficult to do anything that would be like a denial of service attack on the Bitcoin network, right? Because transactions cost money, so you have to spend a lot of money to do this. But the properties of Bitcoin, I can't go into the technical details, but it just kind of protects you against that. But the flip side of that is that it doesn't really scale, right? So you're protecting against denial of service, but it doesn't scale. So then there have been different approaches, different blockchains, different even consensus algorithms other than proof of work that try to deal with this, proof of work being mining, right? And those come with other trade-offs, including some of them are less secure against denial of service attacks and other types of potentially malicious behavior. So there's no free lunch, and it's all being figured out, and that is one of the problems that exists. Go ahead.
As a quick follow-up, I guess, like the solutions that you're deciding today, like, are not applicable to the hardware of tomorrow. Like,
Yeah.
So like something that we might, I assume like they're looking at like the growth of computing computing power because like at some point maybe like Bitcoin's algorithm maybe doesn't work for it.
There's already a quantum blockchain protocol. As far as the DDoS thing, I mean, the whole huge part of this whole thing is everything's distributed.
Yeah.
So you need to attack. If you can hack one blockchain, one person's version of the ledger, you still have another million people to hack.
Sure.
And that's why that's the beauty of it. It's not a central node spoke system. There is no single point of attack. That's
Okay.
Probably time for one more question.
Okay.
That's not us.
Amit, go ahead.
Yeah, so one thing, as you mentioned, like there's a lot of interest from the venture capital community and the entrepreneur, but I haven't seen a lot of investment from like Google, Apple, Facebook, the big tech,
They're doing
the big tech companies.
Uh-huh.
Like, is that true or?
Facebook has announced Facebook.
Yeah, so Facebook has a research group that is doing some blockchain stuff. I would be shocked if all of the major tech companies didn't have like some kind of internal groups at least looking at it. I mean, you know, Amit, that Comcast has a group that's looking at blockchain for stuff. I'm more skeptical of those things for a couple of reasons. One is that it kind of goes back to like what are you doing, right? Like if you're shoving blockchain into an existing application, you're probably doing it wrong, right? And I think that's what a lot of companies are looking at right now, including some of the big ones. The other thing is, I actually kind of think this technology, with the exception of maybe Apple, and I actually just wrote a blog post about that on buildblockchain.tech, with the exception of maybe Apple, I think this technology is actually pretty subversive to the business models that these big tech giants have, right? So, I mean, by definition, Google, Facebook, and to some extent Amazon, their value proposition is that they're centralized services. And these networks are all about decentralizing things. And so I think that in the long term, it's a kind of disruptive technology that might actually pose an existential threat to those companies. And it would be pretty hard for them to adopt it in a meaningful, decentralized way. Maybe they'll try to co-opt it instead. I mean, that would be one tact to try to take. But again, it's why it's so exciting. Like, who knows how all this is going to play out. All right. Well, thanks for the time, everybody.